There was a time when we believed we understood the universe, that everything fit neatly inside familiar numbers and trusted models. Then James Webb opened its eye, and space began to whisper different truths. Galaxies too old for their age. Black holes larger than memory itself. As if the universe had already grown up before we were ready to notice. This video does not only ask how large the universe is, it promises to challenge how we measure existence itself. If you have ever felt that the universe is somehow looking back at you, leave a comment and share your thought. What do you think we have been missing all along? And now, let us step into the first moment, when a telescope becomes a time machine. What if the deepest image we have ever taken of the universe is not a photograph at all, but a memory, returning to us after billions of years of silence? When we look up, it feels like we are seeing a place, a dome of stars, a dark ocean with scattered lanterns. But in truth, we are seeing a timeline. The night sky is a museum where every exhibit is still alive, still burning, still traveling toward us at the speed that nature allows. The moment your eyes meet the glow of a distant star, you are not witnessing now. You are receiving a message that left long before your first breath, long before your ancestors learned to name the constellations. This is the quiet paradox at the heart of astronomy. Distance is time. Space is not merely a stage. It is an archive. This is why the question lands with such weight. When we look deeper into space, are we truly looking backward into the past? In the simplest sense, yes. Light is fast, but it is not instantaneous. A beam leaving the sun takes about 8 minutes to reach Earth. The glow from the nearest star system takes more than 4 years to arrive. The light from a galaxy millions of light years away began its journey before modern humans ever built cities. One gentle way to picture this is to imagine standing on a distant ridge at night and watching a thunderstorm over the horizon. You see the lightning first, sharp and silent, and only later does the thunder arrive, rolling toward you like a delayed voice. Space works like that, except the delay is not seconds, it is centuries, millennia, eons. Another example is more intimate. Think of opening an old family album and seeing a photograph of someone you loved, taken decades ago. The person in the photo is captured in a moment that is gone, yet the image makes it present again inside your mind. Distant galaxies are like that, except the album is the universe itself, and the pages are written in photons. But here the story becomes even more haunting, because the farther we look, the stranger past becomes. We are not simply seeing older versions of familiar things. We are watching the universe in its youth, when it was smaller, hotter, and filled with conditions unlike anything around us today. And when the James Webb Space Telescope stares into that darkness, it does so with a kind of patience that feels almost human. It waits. It gathers. It listens for the faintest whispers of ancient light. It does not merely look outward. It reaches back. Carl Sagan once said, "We are a way for the cosmos to know itself." That line is often repeated, but it becomes something else entirely when you remember what Webb is doing. The cosmos is not only knowing itself through us, it is also showing us its own childhood, inviting our minds into an era we were never meant to witness with naked eyes. And yet we can. Not because the universe became kinder, but because our tools became more sensitive, more precise, more daring. This is where the second question rises naturally. Where does the limit of human observation truly lie, in technology, or in the very structure of the universe? At first glance, it feels like a technological challenge. Build bigger mirrors, cool your detectors, launch above the blur of Earth's atmosphere. wait longer, collect more photons. And yes, progress is real, and the history of astronomy is filled with moments when a new instrument shattered an old boundary. Edwin Hubble pushed the known universe beyond the Milky Way and changed our cosmic address forever. In that spirit, Webb is a continuation of a very old human impulse, to stand at the edge of what we know and lean forward. But the universe is not an endless open field. It has fences that are not built by engineers, but by physics. Some limits come from the fact that light needs time to travel, and the universe has an age. There is a horizon, not a wall of stone, but a boundary of causality. Beyond it, light simply has not had enough time to reach us since the beginning of cosmic expansion. Other limits come from the nature of the early universe itself. There were epochs when space was filled with fog, a hot plasma that scattered photons so thoroughly that light could not travel freely. There were times when the universe was, in a very real sense, opaque. Even the most powerful telescope cannot see through an era that produced no free-traveling light. This is not a failure of human imagination. It is the universe's own condition, like trying to see the seabed through a storm-tossed ocean. And yet, within these limits, there is a key that opens astonishing doors. That key is infrared. Why does infrared become the language of the earliest chapters of existence? Because the universe is expanding, and expansion stretches light the way time stretches a memory. Photons leaving a young galaxy began as energetic ultraviolet or visible light, but as they traveled for billions of years through expanding space, their wavelengths lengthened. The light is not merely traveling, it is being translated. By the time it reaches us, it has been pulled into the infrared, like a song slowed down until it becomes a deeper note. Infrared is also the gentle light that can slip through cosmic dust, the veil that hides newborn stars and the crowded hearts of galaxies. Where visible light is scattered and absorbed, infrared can pass, revealing structures that would otherwise remain sealed behind curtains of cold matter. It is the difference between trying to see a candle through thick smoke and using a wavelength that the smoke cannot easily block. So when Webb looks in infrared, it is not choosing a style of vision, it is choosing the only dialect that the early universe still speaks to us. This is where a famous line from Albert Einstein begins to feel less like a quote and more like a quiet instruction. The most incomprehensible thing about the universe is that it is comprehensible. We are not guaranteed this. There is no cosmic law that says ancient light must carry information in a form that our minds can decode. And yet it does. Hydrogen leaves fingerprints in spectra. Oxygen and carbon write their signatures in absorption lines. The universe marks itself with patterns, and we have learned, slowly and humbly, to read them. Now consider the last question, the one that turns the whole experience into something almost spiritual. If each faraway galaxy is a fossil, what history is being read for the first time? Not merely the history of objects, but the history of emergence. We are watching how simplicity became complexity, how the first gas clouds became the first stars, how the first stars forged the first heavy elements, how those elements became the raw material for planets, oceans, and eventually nervous systems that could wonder why the sky is dark and full of lights. The fossils are not dead. They are messages from the stages of becoming. And what is most moving is that these messages do not arrive as clean answers. They arrive as tensions, as puzzles, as images that refuse to fit into our older expectations. Webb has shown galaxies that appear too bright too soon, structures that seem too mature for their age, black holes that look like they grew faster than our neat narratives allow. This is not a reason to panic or to sensationalize. It is a reminder that nature is always more subtle than the models we build to describe it. The universe is not obligated to match our first drafts. So the educational value here is not just in the facts, as breathtaking as they are. The deeper value is in the method, the posture of mind. We learn to hold the known and the unknown together without forcing closure. We learn to revise without shame. We learn to say, with honesty, that the map was incomplete, not because the explorers were foolish, but because the territory is vast. In that sense, Webb is not merely a telescope. It is a lesson in intellectual humility, delivered in light. And perhaps this is the most beautiful part. When you sit with these ideas long enough, they begin to feel like meditation. You breathe in and imagine a photon leaving a newborn galaxy when the universe was young, traveling through expanding space, slipping past dust, surviving the eras, and finally landing on a mirror made by human hands. You breathe out and realize that the photon's journey and your own are connected, not by mysticism, but by continuity. The same universe that formed those galaxies formed the atoms in your body. The same physical laws that shaped cosmic dawn shape your heartbeat. So as we move forward, keep the hook close, because it is not just a hook, it is a compass. If looking deeper means looking backward, then every new image is also a new question. What else is waiting in the dark, just beyond the edge of our instruments? And when a telescope becomes a time machine, what happens to our sense of now, our sense of here, our sense of what it means to be a brief conscious creature inside a universe that remembers itself through light? What if the biggest surprise James Webb has given us isn't a new object at all, but a new tempo, a different rhythm in the opening minutes of creation? For decades, we carried a quiet assumption like a lantern into the dark. The early universe, we told ourselves, should be a place of simple beginnings. Small, faint galaxies, loosely assembled, still learning how to become. The cosmos was young, almost breathless, only a few 100 million years removed from the first flash of expansion. In that short window, gravity should have been patiently gathering matter, slowly, methodically, like frost forming on a cold pane of glass. And then, Webb looked calmly, relentlessly, in infrared, and the lantern light revealed something that felt almost impossible. Not timid, newborn structures, but galaxies already shining with confidence, already organized, already bright enough to be seen across a gulf of time so vast that the photons arriving in our detectors began their journey before Earth even existed. The question that follows is not merely technical, it's almost psychological. Why do these primordial galaxies look too large, too luminous, too mature for their age? How can complex structure appear when the universe was still in its first few heartbeats? Are we witnessing faster physics in the young cosmos, or are we confronting the hidden weakness of the stories we've been telling ourselves? It helps to remember that astronomy is the art of reading light, like a historian reads fragments of a burned library. When Webb detects a galaxy from those earliest epochs, we are not seeing it as it is now. We are seeing it as it was then. And yet, then, turns out to be stranger than our best expectations. In the standard picture, galaxies build gradually inside scaffolds of dark matter. Gas flows in, cools, forms stars. Mergers happen. Over long stretches of time, systems grow and evolve. That script is not fantasy, it is grounded in the physics of gravity and the behavior of matter. But Webb's earliest images suggest that, in at least some regions, the universe may have been writing with a heavier hand and a faster pen. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." And when you listen carefully, that line doesn't sound like a slogan. it sounds like a warning against complacency. Because when the incredible arrives, it rarely arrives in a way that makes our theories comfortable. It arrives like an unfamiliar melody played on a familiar instrument. The notes are recognizable, but the rhythm is not. So what could be happening? One possibility is that the early universe was simply more efficient than we imagined. In the first few 100 million years, everything was denser. Matter was closer together. The cosmic web, the filaments of dark matter and gas that thread the universe, may have fed young galaxies like rivers feed a delta, continuously delivering fuel. If gas arrives faster, star formation can ignite earlier and burn brighter. And if feedback mechanisms, those regulating winds from supernovae and growing black holes, were weaker or behaved differently at first, the early galaxies might have been allowed to grow quickly without being disciplined into slower development. But even this is not a complete answer, because efficiency alone doesn't always explain maturity. A bright galaxy isn't just a pile of stars. Brightness implies immense populations of young, massive stars, stars that live fast and die young. It implies organized structure, perhaps already rotating, already forming patterns. That's not impossible in principle, but it is surprising in timing. The universe, in those early centuries of millions of years, was like a stage still being built while the actors are already performing. Another possibility is that our assumptions about those first chapters, our initial conditions, are too smooth, too tidy. We often picture the Big Bang as distributing matter almost evenly, with tiny fluctuations that later grow under gravity. But what if, in some places, those fluctuations were stronger than we think? What if certain regions began denser slightly, but decisively, so that gravity had a head start? Even a small advantage, applied early, can compound into a dramatic difference. In that case, Webb may be catching the universe's earliest overachievers, pockets where structure formed unusually fast. Not because the laws changed, but because the starting line was not the same everywhere. And then there is the possibility that pushes us into deeper waters. Perhaps the model itself is incomplete. Not wrong in the way a myth is wrong, but incomplete in the way a map is incomplete. A map can be accurate and still leave out rivers, valleys, and entire mountain ranges. When Webb shows us galaxies that do not fit neatly into our pre-launch expectations, it may be revealing the missing terrain, new details about star formation, cooling, dust, feedback, or the behavior of dark matter in extreme conditions. Here is where a second voice matters, one that keeps our imagination bold but disciplined. Richard Feynman famously said, "I would rather have questions that can't be answered than answers that can't be questioned." That mindset is the spine of real science. Webb's surprising galaxies are not a reason to throw away everything we know. They are a reason to ask sharper questions about what we think we know and why we think it. To make this more tangible, imagine two simple scenes. First, picture a newborn city on Earth, supposedly founded only a year ago, yet already crowned with skyscrapers, highways, and neighborhoods humming with life. Lights in every window, trains running on schedule. It's not that a city can't grow quickly. It's that the infrastructure, the planning, the layers of development imply time. That is what these early galaxies feel like. We expected villages of starlight. Instead, Webb shows us something closer to a metropolis. Now picture a campfire seen from far away across a dark plain. A small fire flickers and fades. But if that fire is fed by a steady stream of dry wood, it becomes a beacon, visible for miles. Early galaxies may be like that fire, gas-rich, continuously fed by cosmic filaments, burning brighter than expected, because fuel keeps arriving. The campfire analogy reminds us that brightness is not only about age, it is also about supply and conditions. Yet the city analogy reminds us that structure implies more than fuel. It suggests organization, a kind of early coherence. And coherence is the real philosophical sting here. Because when we say mature, we are making a human comparison. We are projecting our own sense of development slow, layered, sequential, onto a cosmos that may not share our intuition. The universe does not build the way we build. It does not lay bricks one by one in neat rows. It collapses. It flows. It shocks. It merges. It undergoes phase transitions. It creates order through gravity and turbulence in ways that can look almost instantaneous on the scale of cosmic time. What feels impossibly fast to us might be perfectly natural to the universe. Still, the emotional resonance remains, and we should not pretend it doesn't. There is something humbling about looking at galaxies that existed when reality was young and realizing they appear more confident than we expected. It's as if the universe, from the beginning, had a talent for complexity. As if it did not merely begin, it began with momentum. And that brings us back to the deepest question hidden inside all the others. If the first galaxies were already so radiant, what is the true cadence of cosmic birth? Maybe the early universe was a place where time behaved differently in practice, not in principle. Not because clocks ran differently, but because density and proximity made processes unfold at a pace we are only now appreciating. Or maybe our measurements of brightness and mass are being subtly influenced by factors we are still learning to correct for dust, lensing, compact starbursts, the distribution of stellar masses at birth. Or perhaps the universe is telling us that some of our assumptions, especially the quiet ones we didn't realize we carried, need to be re-examined. In a way, that is the educational gift Webb is offering. Not merely facts, not merely prettier pictures, but a demonstration of how knowledge grows, by meeting reality, by being surprised, by refining the questions, and by learning to live with wonder without turning it into certainty. And the wonder is real, because when you sit with this quietly, almost meditatively, you begin to feel the scale of it, not just in distance, but in meaning. Light left those early galaxies long before our planet formed, long before the first oceans, long before any mind could ask what it meant. And yet it arrives now, into instruments we built with our own hands, into the minds of living people, as if the universe has been carrying a message across time just to reach a moment where it could be understood. So perhaps the question is not only, why were the first galaxies so bright? Perhaps it is also, what does it mean that we are here to notice? If cosmic dawn was not dim and hesitant but brilliant and bold, then the universe's beginning was not a quiet whisper. It was a sudden chorus, a fast unfolding, a kind of awakening. And as we follow Webb's gaze deeper into that ancient light, we may find that the true scale of the universe is not only measured in billions of light years, but in the depth of the questions it awakens in us, questions that do not demand quick answers, but invite us to keep looking, keep learning, and keep listening to the silence between the stars. What if the first great architects of the cosmos were not galaxies at all, but hungry shadows, already ancient in their appetite, already immense, before the first city of stars could even raise its lights? When James Webb looks into the early universe, it doesn't feel like ordinary astronomy. It feels like listening at a door we were never meant to open, because on the other side we find a contradiction with gravity's own bedtime story. We were taught a comforting sequence: gas gathers, stars ignite, galaxies assemble, and only then, at the quiet center, a black hole grows slowly, patiently. like a seed becoming a tree. But Webb has shown us hints of something inverted, systems where the seed appears to be a towering trunk and the forest is barely sprouting. Stephen Hawking once wrote, "Black holes ain't as black as they are painted," and in that playful line is a serious warning. These objects are not merely cosmic sinkholes. They are engines, radiating power, shaping environments, rewriting the fate of matter around them. And John Wheeler, who gave us the very phrase black hole, left us another sentence that feels almost spiritual in its simplicity. Black holes have no hair. He meant that, in the end, a black hole forgets the messy details of what formed it, remembering only mass, spin, and charge. Yet the early universe may be hinting at a different kind of memory, not in the black hole itself, but in the scars it leaves on its surroundings, like a fire remembered by the shape of the forest. So how could a black hole become enormous before a galaxy had time to build many stars? In the modern universe, supermassive black holes and their host galaxies tend to grow together, as if locked in a slow dance. But in the first few 100 million years, time is brutally scarce. Star formation takes processes that are fast on human scales, yes, but not instant on cosmic ones. Gas must cool, fragment, collapse, and ignite, and each step is a negotiation between gravity and heat, order and turbulence. If you demand a billion solar mass black hole early on, you are asking for a feast in a universe that has barely set the table. One path is the familiar one, a stellar seed black hole born from the death of a massive star, then fed by gas at the maximum steady pace nature allows. But even at that limit, the Eddington limit, growth is like climbing a mountain in fog. You can keep stepping upward, but the clock keeps ticking, and the summit keeps receding. To reach supermassive scales so early, everything must go right, continuous fueling, minimal interruptions, no harsh feedback stopping the flow, no chaos tearing the supply line apart. It's possible, but it feels like threading a needle while the universe is still shaking from its own birth. The other path is stranger, and perhaps closer to what Webb is nudging us toward: direct collapse. Imagine a vast cloud of pristine hydrogen and helium, not yet enriched by generations of starlight, falling inward as a single decision, refusing to fragment into ordinary stars, collapsing instead into a black hole that begins life already massive. In this scenario, the universe doesn't plant a seed, it drops a boulder into the river and lets the current shape everything around it. The requirements are special conditions that suppress fragmentation, environments that keep the gas hot enough to avoid breaking into star-forming clumps, radiation fields that alter chemistry, flows that are dense, coherent, and relentless. These are not everyday places, even in a young universe, but they may have existed at the nodes of the cosmic web, where filaments feed matter into growing structures like invisible arteries. Now consider the second shock. What happens when a black hole is not a small tenant at the center of a galaxy, but a dominant presence so extreme that it accounts for about 10% of the host's stellar mass? In a human body, that would be like a heart weighing 1/10 of everything you are, a beautiful impossibility. Yet in cosmic terms, it means the black hole is not merely sitting in the middle, it is ruling the climate. As matter spirals into it, it heats, brightens, and blasts energy outward. This feedback winds, radiation pressure, jets, can push gas away, heat it, ionize it, or stir it so violently that star formation struggles to proceed. A galaxy can be rich in fuel and still fail to turn that fuel into stars if the furnace in its core keeps boiling the pot. Here's a way to picture it. Think of a small town trying to grow around a roaring industrial plant that arrived first. The plant provides energy, yes, but it also fills the air with heat and turbulence. The town can't build quietly. Every time it tries to expand, the ground shakes, the air burns, and the materials scatter. Star formation is a kind of construction project, delicate, dependent on cooling and calm. A black hole that turns on too early can make the environment hostile to that calm, keeping the galaxy compact, underdeveloped, and strangely stunted in stars, even while the center blazes. Another example, even simpler. Imagine trying to light candles in a windy room. The wax is ready, the wicks are there, but the gusts keep snuffing the flame before it can stabilize. In the early universe, gas is the wax, gravity is the hand, and star formation is the flame. An overactive central black hole is the wind. It doesn't need to destroy the materials to prevent the candles from catching. It only needs to keep the environment unsettled. And this is where the story becomes beautifully ambiguous, because the same feedback that could suppress star formation later may not prevent black hole growth earlier. A black hole can have a brief, furious growth window, when gas floods inward faster than feedback can push it away. During that window, the black hole gains mass rapidly, like a storm drinking the ocean. Then, when the feedback finally builds into a gale, it shuts the inflow down and star formation along with it. In that sequence, you get exactly the kind of mismatch Webb hints at. A black hole that is already immense, inside a galaxy that looks too small for it, as if the universe built the engine first and only later assembled the vehicle around it. But could some black holes have been born big, not merely growing fast? That possibility changes the emotional tone of the cosmos. It suggests that the early universe may have produced primordial giants, not in the sense of myth, but in the sense of initial conditions. Rare places where matter fell inward without hesitation, where the usual path towards stars was bypassed, where gravity wrote a different first sentence. If that is true, then supermassive black holes are not always the end product of long evolution, they may sometimes be the opening act. And if black holes appear first, do they shape galaxies or restrain them? The answer may be yes, both, like fire. Fire can clear a forest, and it can also make soil fertile. It can destroy, and it can prepare the ground for a new pattern. A black hole's feedback can blow gas out, but that gas does not vanish. It may enrich intergalactic space, seed other regions, fall back later, cool later, build later. Suppression now can become structure later. The galaxy's history might be written in phases. A bright, violent infancy dominated by the black hole, followed by a calmer adolescence where stars finally take over, slowly restoring the more familiar balance seen in the modern universe. This is why the question is not merely how did the black holes grow so fast, but what does fast even mean in the first billion years? We are used to thinking of time as a generous river, but cosmic dawn is a narrow stream, and everything that forms there must do so under pressure. Webb is showing us that the early universe may have been less like a quiet nursery and more like a stormlit coastline. Waves of gas crashing along filaments, mergers happening often, matter piling up where the web knots, and in those knots, the shadows growing quickly enough to outpace our expectations. In the end, these discoveries don't have to be treated like a crisis. They can be treated like an invitation. An invitation to widen our models, to refine our assumptions, to remember that the universe is not obligated to be simple just because we prefer simple stories. Perhaps galaxies and black holes did not always grow together. Perhaps the earliest epoch had its own rules of rhythm, its own tempo of collapse, its own balance between light and shadow. And maybe that is the deeper, quieter lesson. Hiding inside this cosmic puzzle, we look up and expect a neat genealogy stars first, then galaxies, then black holes. But the universe may have written its family tree in another order, as if it began with the heart before the body, the center before the spiral arms, the darkness before the city of lights. If that is true, then Webb is not just showing us distant objects. It is showing us how fragile our narratives are, and how vast the unknown still remains. So I'll leave you with a final question to carry into the silence after this segment ends. If the earliest galaxies were shaped by black holes that arrived first, if the shadows were the first architects, then what else in our cosmic story has been happening in reverse? Quietly, patiently, waiting for us to look again. What if the smallest red specks in James Webb's deepest images are not background noise at all, but a message from the universe's childhood? An encrypted clue, waiting for us to learn its language. When astronomers first began calling them little red dots, the names sounded almost apologetic, like a label placed on a mystery before anyone truly understood what it was. And yet, the more we stare, the more these compact crimson points feel like the universe clearing its throat. They are small, dense, and strangely bright. They glow as though something inside them is burning with intention, but the light does not behave politely. It arrives with contradictions stitched into its spectrum, signatures that resemble vigorous star formation, fresh, hot, youthful, mixed with the telltale fingerprints of a black hole feeding at the center, violent and mature, like thunder under a lullaby. That double identity is the first fracture line in our expectations. In the nearby universe, we often separate these stories. A galaxy is a place where stars are born in sprawling arms and dusty nurseries. An active black hole is a compact engine that can outshine its host, carving winds through gas and rewriting the galaxy's future with feedback and heat. But these little red dots seem to refuse the separation. They look like a newborn wearing an adult's shadow. They look like a candle and a furnace occupying the same matchbox. And if that is true, then the question isn't merely, what are they? The deeper question is, what phase of cosmic evolution have we been missing because we never had eyes like Webb's before? There is a quiet educational value here that goes beyond any single object. The early universe was not a calm museum display. It was a storm of firsts. Gas was streaming along invisible filaments, gravity was gathering matter into knots, and the rules were the same, yet the outcomes were more extreme than our instincts. That's why these little red dots matter. They sit at an intersection of processes we care about most: how the first galaxies assembled, how the first massive black holes appeared, and how energy shaped the growth of everything that came later. To make sense of them, imagine two ordinary scenes. First, picture a brand new city being built on a coastline. You expect to see scaffolding, cranes, half-finished streets, and lights flickering on one neighborhood at a time. Now imagine arriving on the first week of construction and finding a fully lit downtown, bright towers, heavy traffic, a roaring power plant, yet the surrounding neighborhoods are still just foundations. That is what an overactive nucleus inside a small, compact host can feel like. The power plant is the black hole's accretion flow, converting infalling matter into radiation with astonishing efficiency. The half-built neighborhoods are the still-forming stellar populations. The city exists, but the proportions are strange, as if the engine arrived before the streets. Now a second scene. Think of a campfire in dense fog. The fire's glow makes the fog look redder and thicker than it truly is. You might mistake the fog for smoke, or the smoke for fog, because the light is changing what you believe you're seeing. In the early universe, dust and gas can play a similar trick. A heavily obscured quasar can masquerade as something smaller and redder, A compact starburst can mimic an active nucleus. One reason these objects remain slippery is that nature is presenting us with layered light, starlight, black hole light, and the filtering veil of dust, all braided into a single point. That is why the spectrum becomes the courtroom. Spectra are not pretty pictures, they are testimony. When Webb splits the light, it reveals broad features that suggest gas moving at thousands of kilometers per second near a central black hole, alongside narrower features that hint at star-forming regions. The coexistence can be read in multiple ways, and each interpretation teaches something. One possibility is straightforward in concept, even if complex in detail. These are dust-enshrouded quasars, supermassive black holes already active, but wrapped in enough dust that their usual blue-white blaze is muted into a warm red glow. If that is true, the lesson is sobering. It would mean the early universe produced massive black holes quickly and frequently, and many of them were hidden behind curtains we never knew to pull aside. The universe may have been louder than our earlier telescopes could hear. Another possibility is more intimate and, in a sense, more beautiful. That the little red dots mark a transitional stage, an adolescence of galaxies when the first central black holes ignite. At the same time, the host is still building its stellar body. In this picture, the galaxy is not yet the calm spiral we imagine. It is a compact, gas-rich knot, forming stars in bursts, while the black hole feeds greedily from the same reservoir. For a brief window, both processes run together, like two hearts beating out of sync inside the same chest. Then, feedback begins. The black hole's energy pushes, heats, and disrupts the gas. Star formation falters, the object evolves, the phase ends. If this is correct, we may be catching a short-lived moment that is usually gone before a typical cosmic snapshot can see it. And that brings us to the most consequential question. Could this be the missing link in the story of how galaxies and black holes co-evolved? In the modern universe, we often talk about a relationship between the mass of a galaxy's stars and the mass of its central black hole. It is as if galaxies and black holes negotiate a long contract, keeping each other in proportion over billions of years. Yet the early universe seems to contain systems where the black hole is ahead of schedule. The little red dots might be the chapter where the contract was written messy, improvised, full of revisions before it became the tidy relationship we see nearby. This is where a line from Carl Sagan lands with particular force. Somewhere, something incredible is waiting to be known. Because what Webb is showing us is not merely new objects, but new timing. The universe is telling us that order can emerge early, that engines can ignite before frameworks look complete, that what we assumed was gradual might sometimes be abrupt. Stephen Hawking offered another reminder that fits this mood. Remember to look up at the stars and not down at your feet. It's not a slogan about optimism. It's an instruction about humility. The cosmos is not obliged to match our first drafts. When we meet anomalies like these, the scientific response is not panic and not hype. It is patience measurements, cross-checks, better samples, deeper spectra, and the willingness to let the universe correct our metaphors. So, what are these little red dots, really? They might be obscured quasars hiding in dust like embers under ash. They might be compact starbursts with unusually intense conditions. They might be galaxies caught in a rare growth spurt where black holes and stars feed from the same inflow at the same time. They might even represent multiple populations that we have carelessly grouped under one nickname. The honest answer, for now, is that they are a question dressed as a point of light. But even before we solve them, They are already teaching us how to think. They teach us that classification is not understanding. They teach us that the early universe is not a simple miniature of today's universe. It is a different landscape, hotter, denser, faster, where familiar physics can produce unfamiliar outcomes. And they teach us that when we finally build an instrument capable of seeing the ancient dawn, the first thing we meet is not certainty, but complexity. And perhaps that is the most human part of this story. We used to imagine the past as simpler. We used to imagine beginnings as quiet. Yet the universe's earliest scenes appear crowded with activity-red points, feeding cores, newborn stars like a shoreline at night, dotted with fires, each one telling a different story of survival and growth. If these little red dots truly are a missing link, then we are witnessing not just objects, but a transformation. The moment when galaxies learn to live with the gravity at their center, the moment when black holes stop being merely endings and become architects of beginnings. So the next time you see one of those tiny crimson points in a Webb image, don't think of it as a dot. Think of it as a doorway. A small, red-lit threshold in the distance, where the universe is still deciding what it will become and where we, watching from billions of years later, are finally beginning to understand the question it has been asking all along. How early did the universe begin to organize itself? Not as a smooth fog of matter, but as a living architecture of threads and knots, of luminous islands separated by immense silence. And if that pattern was already taking shape so soon after the beginning, what does it say about the kind of cosmos we inhabit? When we look up on a clear night, the sky gives the impression of randomness, a scatter of lights thrown across a dark dome. But the deeper our instruments look, the more that randomness dissolves into structure. Galaxies are not sprinkled like salt. They gather, they align, they form chains, walls, and filaments that stretch for hundreds of millions of light years, and between them open voids so vast that the human mind struggles to keep them in focus. This is what cosmologists call the cosmic web. But the phrase can sound too tidy, too domestic, for something so immense. It is more like the grain in ancient wood, the hidden pattern inside stone, the faint memory of a force that shaped everything before anything had a name. The astonishing part is not merely that the web exists, it is how early it began. In the oldest light we can measure, the cosmic microwave background, we find tiny differences in density, barely 1 part in 100,000, a slight unevenness in what should have been perfect symmetry. Those faint ripples are like fingerprints left on the universe while it was still an infant, and from them over time gravity did what gravity always does. It amplified small differences into large destinies. Regions a little denser pulled in more matter. Regions a little emptier fell behind. And slowly, inevitably, a cosmic geography emerged. Here, a filament. There, a node. And beyond them, a quiet hollow where almost nothing gathered at all. But if gravity is the sculptor, dark matter is the unseen clay. It is one of the strangest truths of modern astronomy that most of the matter in the universe does not shine. It does not glow. It does not absorb light. It does not speak in any wavelength our instruments can directly hear. And yet, without it, the visible universe makes less sense. Galaxies would have trouble forming as quickly as they did. Clusters would not hold together as tightly as they do. The web would be thinner, later, and perhaps never quite complete. Dark matter, whatever it is, behaves like a vast invisible framework, an underlying skeleton guiding ordinary matter, the way a riverbed guides water. You may not see the riverbed from above, but you can read its presence in the flow. Vera Rubin, whose work helped convince the world that dark matter is real, once captured the feeling of this discovery in plain human terms. It is a strange world, and it is, because once you accept that most of reality is invisible, you begin to suspect that the universe has been shaped by forces we can only infer, like wind revealed by moving leaves. Imagine, for a moment, a city seen from an airplane at night. The lights do not fill the landscape evenly. They gather along roads and coastlines, clustering into bright downtown cores, thinning into suburbs, and then fading into rural darkness. Now imagine you could not see the roads at all, only the lights. You might still guess that some hidden structure is guiding where the lights can be. That is what astronomers do with dark matter. They see the lights of galaxies and the glow of gas, but they infer the invisible roads beneath them, the filaments of dark matter where gravity has quietly done its patient work. And here, the story deepens, because location is not just a coordinate on a map. In the cosmic web, location can feel like fate. A galaxy born near a filament may have a steady supply of cold gas streaming in along that invisible corridor, fueling star formation like a slow, reliable breath. A galaxy born near a node where filaments intersect may live in a busier neighborhood, surrounded by companions, pulled into mergers and interactions, its shape and history altered by repeated encounters. Meanwhile, a galaxy drifting in a void may live a quieter life. Fewer collisions, fewer tidal disturbances, less gas arriving, a slower pace, a longer solitude. Not better or worse, just different. Like the difference between a town at a crossroads and a cabin far out in the desert. This is not mysticism. It is environment. It is gravity and supply lines and probability. And yet, when you step back far enough, it begins to resemble something almost philosophical. The idea that the largest structures in the universe can influence the smallest personal histories of stars, planets, and perhaps, eventually, life. To make it more tangible, think of a spider web after morning dew. The strands are nearly invisible until the droplets reveal them, and suddenly the whole design appears, delicate and intentional. In the cosmic web, galaxies are like those droplets. They make the invisible visible. They show us that space is not an empty stage where matter randomly performs, but a structured arena, shaped by an unseen hand we call dark matter, and governed by laws that operate with breathtaking consistency. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." That line feels especially true here, because every time we map the cosmic web more precisely, we learn that the universe was not waiting until late times to form structure. It was organizing early, as if the blueprint was already folded into the initial conditions, those faint ripples in the newborn cosmos that later became the seeds of everything we see. And this is where the final question begins to shimmer with meaning. If order appeared so early, was it programmed from the start? The careful answer is that physics does not require intention. A small set of simple rules can create astonishing complexity. Snowflakes do not have goals, yet they form intricate symmetry. Sand dunes do not plan their curves, yet wind and gravity shape them into repeating forms. In the same way, the cosmic web may be the natural result of gravity acting on tiny early fluctuations, amplified over billions of years. No designer needed, only lawful processes given time. But that does not make it less mysterious. In some ways, it makes it more mysterious. Because then the question becomes, why were those initial ripples there at all? And why do they have the particular pattern that leads to a universe capable of galaxies, stars, chemistry, and consciousness? We can describe the evolution of the web with simulations and equations, and we can match those predictions to observations with increasing confidence. But the deeper why remains like a soft echo in the background. There is another example that brings this closer to the human scale. Pour a little cream into black coffee and watch what happens. At first, it looks chaotic, white tendrils curling into darkness. But then patterns appear, filaments, knots, branching structures, a brief, beautiful architecture that forms naturally from flow and mixing. The cosmic web is like that, except the coffee is space itself, the cream is matter, and the stirring spoon is gravity operating over unimaginable time. What looks like chaos from too close becomes structure from far away. And once you see that, you begin to understand that the web is not merely a feature of the universe. It is the universe's memory of its own beginning, still visible in the arrangement of everything. So when we ask how early the web formed, we are really asking how quickly the universe learned its own shape. When we ask what dark matter does, we are asking what invisible foundation holds the visible world in place. When we ask whether a galaxy's position determines its fate, we are asking whether environment, supply, and interaction write destinies on scales too large for any single star to resist. And when we ask whether order was programmed from the beginning, we are touching the oldest kind of question, the one humans have asked in temples, in deserts, and under night skies long before telescopes existed. Is reality unfolding by chance, or by a deeper necessity we have not yet learned to name? Perhaps the most honest response is to hold both feelings at once, the clarity of science and the humility it demands. The cosmic web can be explained, yes, but it can also be contemplated. It is a reminder that we live inside a structure we did not build, shaped by forces we cannot see, and connected through filaments of history back to the first tremor of creation. And as we continue, the next step is unavoidable, because once you recognize the web, you start to wonder about the lights caught inside it. What those earliest galaxies looked like, how quickly they ignited, and what they reveal about the true scale of the universe we thought we already understood. What, really, switched on the universe, the first stars, or the first galaxies? It sounds like a simple choice, like deciding whether a lamp is lit by its filament or by the room that holds it. But cosmic history is rarely that polite. In the beginning, there was no night sky the way we imagine it now. No familiar scattering of points above a dark horizon. There was, instead, a young universe thick with hydrogen, a vast, cold ocean of atoms that loved to swallow energetic light. Even if something tried to shine, the light did not travel far. It was like striking a match inside a deep fog. The flame exists, but its reach is short, and the world beyond remains hidden. So when we ask who truly lit the cosmos, we're also asking who changed the medium itself. The first stars may have been the sparks, but the first galaxies may have been the wind that turned those sparks into a lasting dawn. A single star can carve a bubble of clarity around itself, ionizing hydrogen, making a small region transparent. But a galaxy is a chorus. A galaxy is not one candle. It is thousands, millions, sometimes billions of candles breathing in rhythm, pouring ultraviolet light into the surrounding dark. The difference between a lone voice and a choir is not just volume, it is inevitability. Enough light, sustained long enough, does something profound. It changes the rules of visibility. This is why light in cosmology is not merely illumination. Light is chemistry. Light is architecture. Light is a force that reorganizes matter without touching it directly. When the first luminous objects ignited, They did not simply decorate the universe, they transformed it. Neutral hydrogen, once a veil, became a window. The cosmic dark ages were not darkness in the human sense, but opacity, a universe whose atoms were arranged in a way that made long-distance starlight difficult to survive. Then the first intense radiation arrived and began to unmake that opacity. Hydrogen atoms were split again into protons and electrons. Ionized gas does not absorb ultraviolet light the same way. Suddenly the fog thinned. The universe, in a very real physical sense, became more transparent. It became readable. Here is the first example that makes the scale of that transformation easier to feel. Imagine a shoreline before sunrise. The air is cool and heavy with mist. You can hear waves, you can smell salt, but the horizon is erased. Then the sun rises, not with a sudden blast, but with a gradual insistence. At first you see only a faint brightening, then shapes appear. The mist begins to loosen its grip. The world does not change because the beach is rebuilt. The world changes because the medium between you and the beach becomes clear. Reionization was like that, not the creation of matter, but the clearing of the cosmic air. The universe did not gain new continents, it gained visibility. And this is where an old, famous line becomes more than poetry. Carl Sagan once said, "We are made of star stuff." In the context of the first light, it's also a statement about inheritance. The first luminous objects didn't only reveal the universe, they altered it, seeded it, and set the conditions for everything that could follow. Without early stars forging heavier elements, and without early galaxies distributing those elements and radiation, the later universe would be a different kind of place entirely. Not just darker, but chemically simpler, more limited in what it could build. Yet the story grows even more humbling when we look at explosions that happen near the edge of time and discover they obey the same underlying rules as the stellar deaths we observe today. There is something deeply steady about the cosmos in that realization. A star collapses, matter rebounds, energy races outward, elements form, and light carries the signature across billions of years. When modern instruments watch a supernova from a time when the universe was still young, the spectrum can look eerily familiar, as if the universe has been rehearsing the same physics since the very beginning. That continuity raises a question with almost spiritual weight. If the laws of nature do not change, why did the early universe behave so differently? The answer is not that the universe rewrote its rules, but that it changed its conditions. Think of it this way. The same musical notes can produce a lullaby or a thunderous anthem depending on the room, the instruments, and the number of voices. Gravity is gravity, but gravity inside a dense, gas-rich, rapidly evolving early cosmos produces different outcomes than gravity in a calmer, older universe. Electromagnetism is electromagnetism, but electromagnetism operating in pristine hydrogen and helium with almost no heavier elements creates stars that form, live, and die under different pressures than stars today. Here is the second example. Imagine using the same recipe in two kitchens. In one kitchen, you have modern appliances, steady temperatures, and refined ingredients. In the other, you're cooking in a wind-battered hut, using coarse flour and an unpredictable flame. The recipe is the same. The physics of heat and chemistry is the same, but the result can be wildly different. The early universe was that second kitchen. The ingredients were pristine, the cooling pathways were limited, the gas was abundant, the structures were smaller and denser, the interactions more frequent. Under those conditions, stars could be more massive, radiation more intense, feedback more dramatic. The laws stayed constant, but the universe expressed them in a different accent. This is also why light had the power to change everything. Light is not passive. High-energy light in particular is a sculptor. It heats gas, it ionizes atoms, it pushes on dust, it triggers winds. It can shut down star formation in one place and ignite it in another. In the young universe, where gas was the primary fuel, and the cosmic web was still assembling its first strong filaments, light became a kind of organizing principle. It did not merely reveal the structures, it helped decide which structures could endure. A bright source does not only announce its existence, it influences the future of its neighborhood. And perhaps that is the quiet lesson hidden inside these questions. We often talk as if the universe is a stage and light is the spotlight. But in cosmic history, light is also part of the cast. It shapes the drama as it unfolds. There is a line often attributed to Neil deGrasse Tyson that lands with special force here. The universe is under no obligation to make sense to you. But there is a companion truth that feels equally important. The universe is under no obligation to remain mysterious forever. It yields, slowly, to patience, to better instruments, to careful thinking. And when it yields, what we find is rarely the tidy answer we expected. Instead, we find layered causality. The first stars ignited, yes. The first galaxies amplified that ignition, yes. The light changed the state of matter, yes. The laws stayed the same, yes. And still, the early universe does not look like a smaller version of the present. It looks like a different world. Not because the rules changed, but because the universe was young enough for the same rules to produce stranger outcomes. So when you imagine that ancient epoch, try not to picture a quiet emptiness slowly filling with familiar things. Picture something more alive. Picture a universe learning how to become transparent. Picture islands of ionization expanding like clearings in a forest of fog. Picture newborn galaxies burning bright, not as ornaments, but as engines. Picture stars dying and being reborn in a cycle that would eventually create carbon in your blood and iron in your bones. We are made of star stuff, yes, but we are also made of cosmic timing, of early conditions, of a long chain of transformations that began when the first light did more than shine. It changed what the universe could be. And now, sitting here in the late calm of cosmic history, we can ask one last question that lingers like a bell in a quiet room. If the first light transformed the universe from opaque to transparent, from silent to readable, what transformations might still be ahead, waiting in the darkness we have not yet learned to see? What if the edge of the universe is not a wall at all, but a mirror that simply refuses to reflect anything we are not yet ready to understand? For most of human history, we have lived with a comforting illusion that the world is bounded, that if we travel far enough or build a powerful enough instrument, the unknown will finally end and knowledge will begin. Yet every era has discovered the same unsettling truth. The horizon moves. It moves for the sailor who reaches the last visible line of the sea. It moves for the astronomer who reaches the last visible galaxy. And now, with James Webb and the telescopes that will follow, we find ourselves asking a question that is both scientific and strangely intimate. Are we truly approaching the final boundary of observation, or are we only brushing against the temporary limits of our tools? Webb has done something astonishing, not because it has solved the universe, but because it has made the universe feel alive again, like a vast landscape that keeps changing shape as the light changes. It is easy to forget that an edge in cosmology is not like the edge of a continent. It is not a cliff. It is a limit defined by time itself, by how long light has been able to travel since the beginning of cosmic expansion. The most distant galaxies we see are not simply far away. They are young. They are ancient. At the same time, they are the universe in its earliest handwriting. And when we push beyond them, we do not hit a wall. We step into chapters where there were no stars at all, only cooling gas, only a darkness that was not empty, but unlit. Carl Sagan once reminded us, somewhere, something incredible is waiting to be known. That line has been repeated so often it can sound like a slogan, but it endures because it is not really about astronomy. It is about humility. It is the recognition that the universe does not owe us clarity. It offers clues, and it offers silence, and it is our task to learn the difference. When we ask whether we are nearing the ultimate edge of observation, we are really asking whether reality has a final surface, or whether our perception simply has a final depth. The honest answer is that the universe contains both kinds of limits. There are limits built into physics and limits built into us. One of the simplest examples is also the most haunting. Imagine standing in a desert at night, holding a lantern. The lantern does not reveal the desert's boundary. It reveals only the radius of your own light. Beyond that radius, there may be dunes, mountains, a distant city, or nothing at all. But the darkness does not tell you which. In the same way, the observable universe is not a map of everything that exists. It is the radius of the cosmos's lantern, the distance that light has had time to cross. We can build a better lantern. We can make it more sensitive. We can tune it to infrared, to radio, to gamma rays. But we cannot make it shine beyond time. Not yet. Perhaps not ever. And yet, technology does move horizons. We have already lived through that transformation once. Hubble expanded the visible universe like a curtain being pulled back. Webb is doing it again, but with a deeper color palette, because the early universe is redshifted into wavelengths that older eyes could not see. Each new instrument is like learning a new language. When you learn it, reality does not change, but what you can notice changes, and that difference can feel like a revelation. The galaxies that look too bright, too mature, too early, are not only a challenge to models, they are a reminder that the universe has always been more creative than our expectations. So what lies behind the first galaxies, beyond the faint red smudges that mark the frontier of starlight? Is it merely darkness and silence? Or is it a structure we cannot yet name? Here we have to resist the temptation to dramatize the unknown as emptiness. The so-called cosmic dark ages were not a void. They were a phase, a state of matter and radiation before the first luminous objects ignited. Space was filled with neutral hydrogen, cooling, drifting, responding to gravity's patient pull. There may have been subtle patterns, the earliest scaffolding of the cosmic web, already forming, already guiding where future galaxies would gather. If you could see in wavelengths we have not yet mastered, perhaps the darkness would look textured, like a fog that carries hidden currents. The silence might have its own faint music. Stephen Hawking once said, "Look up at the stars and not down at your feet." It is a beautiful line, and it carries a quiet instruction. To look up is not only to stare at glittering points. It is to accept that the universe is larger than our immediate concerns, and that our minds are capable of stretching into that largeness. But Hawking also spent a lifetime studying the ways the universe hides itself, through horizons, through black holes, through the limits of information. In cosmology, behind, the first galaxies may not mean behind in space, but behind in time. To see earlier than the first stars is to see a universe that cannot easily announce itself in light. That does not mean it is unknowable. It means we must become more patient, more inventive, more precise in the questions we ask. A second example helps ground this. Think of archaeology. When you excavate an ancient city, you do not dig until you hit the end. You dig until the soil changes, until the layers tell you that you have reached a time before human settlement. Below the first bricks there is still a story, just a different kind, a story of rivers, climate, geology. The absence of pottery does not mean the absence of history. It means history has changed its language. In the same way, beyond the first galaxies, the universe's story continues, but it may be written in hydrogen's faint absorption, in the leftover glow of the cosmic microwave background, in gravitational waves, in patterns of matter that do not shine. Our job is to learn to read those scripts. And then comes the question that makes all of this feel personal. Will the universe expand forever? Or is it moving toward another transformation? On the largest scales, the evidence points to an expansion that is not slowing down, but accelerating, driven by what we call dark energy. That phrase is both a label and a confession. It is our way of saying we have measured an effect without fully understanding its cause. The sober scientific view is that the expansion could continue for unimaginably long periods, thinning the cosmos, carrying distant galaxies beyond any future horizon, leaving local groups isolated like islands in a dark sea. But cosmology also teaches us to be careful with forever. The universe has already changed phase more than once. Plasma cooled into atoms. Darkness yielded to stars. Neutral gas became ionized again. Each transition reshaped what was possible. It is not unreasonable to wonder whether another transition waits ahead, subtle or dramatic, whether dark energy is truly constant or an evolving field, whether gravity behaves differently over immense distances, whether the fate of expansion is a story still being written. And that leads us to the final question, perhaps the most unsettling and the most beautiful. Are we discovering the universe, or are we slowly remembering ourselves? Because every time we extend our reach, we do not only find new objects, we find new perspectives on what it means to be here. The universe is not a backdrop, it is a process. And we are not outside that process, taking notes from a safe distance. We are made of the very elements forged in ancient stellar deaths. The atoms in your hands were not born on Earth. They were assembled in stars that lived and died long before our sun existed. When Webb looks back toward cosmic dawn, it is not only peering into an alien past, it is peering into the earliest conditions that eventually made our existence possible. In that sense, cosmology is a kind of memory work. Not memory in the sentimental sense, but memory in the physical sense. The way matter preserves its history in its composition, the way light preserves its history in its wavelength. There is a quiet, meditative dignity in admitting that the universe may not have a final edge we can reach. Perhaps the true scale of the universe is not a number we will ever hold comfortably in the mind. Perhaps it is a relationship between what exists and what can be known, between the questions we ask and the instruments we build, between the vastness outside us and the vastness within. We push outward, and the horizon retreats. We refine our theories, and the universe offers exceptions. We search for certainty, and we encounter mystery, not as an enemy, but as a teacher. So if you find yourself moved by these questions, not frightened but quietly awakened by them, stay with me. Because the next part of this journey begins where the universe becomes most strange and most honest, at the point where distance turns into time, and observation turns into a kind of listening. We are going to step into that moment now, when the telescope stops being a tool of sight and becomes something else entirely, a machine that lets us touch the past without ever leaving the present. As we reach the end of this journey, one quiet truth begins to settle. The universe has not become smaller or more understandable simply because we have looked deeper. Instead, it has grown more subtle, more layered, more patient than we ever imagined. Each discovery made by James Webb does not close a chapter, it opens another, reminding us that knowledge is not a destination but a continuous widening of perspective. The galaxies that appeared too early, the black holes that grew too fast, the darkness that was never truly empty, all of them teach the same lesson in different forms. Reality is richer than our models, and humility is as essential to science as curiosity. What we take from this is not certainty, but orientation. We learn how to ask better questions, how to listen more carefully to what the universe reveals and what it withholds. In doing so, we also learn something about ourselves, about our place in a cosmos that does not revolve around us, yet somehow produced us. That realization carries a quiet power. It invites patience, wonder, and respect for the unknown. To everyone who stayed with this exploration, thank you. Your attention, your curiosity, and your willingness to think deeply are what keep these conversations alive. If this journey left you with a sense of awe or reflection, then it has already achieved something meaningful.